Okay, so as I promised, I'm going to do this one about the last question on the Chapter 3 homework, problem 19, also 3.80 out of the book. And what we see in this problem is we have an acceleration of a particular car during braking. So a car braking has magnitude bt, where t is the time in seconds from the instant the car begins braking, and b is 2.5 meters per second cubed. Okay, and the question we're trying to answer is, if the car has an initial speed of 45 meters per second, how far does it travel before it stops? Okay, this is interesting. Magnitude bt, but it's braking, and it's going to stop. Let's keep all those things in mind as I move over to the whiteboard. So the acceleration has a magnitude of bt. That's not the vector, that's just how big it is. It's got an initial velocity, the initial of 45 meters per second. And it's stopping. So that means the final velocity when we're done is going to be 0. We don't know how much time it takes. We don't know how far it's going to travel. In fact, how far it's going to travel is exactly the thing we're trying to answer. So this is the thing we're looking at. We're trying to figure out that. What is delta x? But we also don't know how much time it takes for it to stop. Okay, so if the initial velocity, let's write this as a vector. If the initial velocity is positive, let's say it's in the I hat direction, then the acceleration magnitude doesn't quite tell us what we want. We also need to know that because the direction was positive to the right and it's slowing down, that means the acceleration's got to point in the opposite direction, back to the left. That means that the vector for the acceleration has got to be negative bt, whatever that is, I hat. And the problem says that b is 2.5, so that's negative 2.5 t I hat. So I'm going to leave it as a b for most of the work here. So that's interesting because the acceleration is not constant. The fact that there's a t in there means that the t matters for determining how big the acceleration is. It's getting bigger with time, or a larger magnitude of acceleration. So that's like you're slowing down at one rate at first, but then you push harder on the brake as you slow down. So let's sketch some graphs of what that looks like. So that means that the acceleration graph is going to look like, we've got a and t. The acceleration starts at 0 at time 0 and increases at a steady rate. Okay, where the slope of this is b. Slope equals b. So that's a not constant acceleration. Okay, what does that mean about the velocity graph? The velocity is going to be decreasing. It starts at 45. It's going to end at 0. And is it going to be flat at first and then steeper later because it slows down faster later? Or is it going to be steep at first and then less steep later on because it's slowing down faster at first and then more and then less later? Well, because the magnitude of the acceleration keeps increasing, that suggests that the braking power, like the change in speed, is not very big at first, and then it gets bigger and bigger and bigger over time. So you have a curve down like that. Okay. And that kind of makes sense if you're thinking about adding up the little areas of this acceleration graph. If you add up all those little pieces, that tells you how much the velocity changes during that time frame, and that makes it go farther each moment. Okay, and then we also want to do a position graph. So the position graph, it's going forward and it's slowing down. So, and it's fastest at first, so it's steepest at first, and then slows down later. Yeah, but then the rate of change is faster later. So I'm not quite sure what that's going to look like. You have to think about that one. Something like that. So it's a cubed graph. Okay, so we're going to do that same progression that we did before for other problems where we're doing integrals to figure out what the velocity and position functions are. So we know that the acceleration, the function is negative bt, and we know that the velocity is the integral of a dt. So the velocity is the integral of negative bt dt, which is negative 1/2 bt squared plus a constant. And we know that the velocity at time 0 is 45, which is negative 1/2 times b times 0 squared plus a constant. So that means the constant is 45. So the velocity function is 45, oops, 45 minus 1/2 bt squared. Okay. Well, I notice that over here, I didn't know how much time it's going to take to stop. Delta t equals, I don't know. But this function tells me what the velocity is at any moment in time, so I could use that to figure out how much time it's going to take for it to stop. Why don't I do that? So the velocity when it stops is going to be 0. So v at some later time is 0 equals 45 minus 1/2 bt squared. So I'm asking the question now, at what moment in time is the velocity equal to 0? So I solve that, you get negative 45 equals negative 1/2 bt squared. Multiply the 2 over to the other side and the negative, and you get 90 over b equals t squared. And the b in this case is 2.5, so t squared equals 90 over 2.5. And then you work out what the square root of that is, and you get that the t is 6 seconds. Cool. So as that braking power increases, you slow down faster and faster. So in the first second, you slow down by 2.5 meters per second. And then in the second second, you slow down by 5 meters per second. And then in the third second, you slow down by 7.5 meters per second. And the fourth, you slow down by 10 meters per second. And that keeps adding up. So it only takes 6 seconds total to slow down to 0. All right. Okay, so I just moved the board over a little bit and got myself a little more space so that I can now use this information about the velocity to figure out how far it travels during that time. So I have the velocity function, 45 minus 1/2 bt squared, right there. And I want to figure out the position function. So I know that the position is the integral of v dt, which is the integral of 45 minus bt squared dt, which is 45t minus, oh, I dropped the 1/2. 1/2 minus bt squared over 6. That's from the 1/3 and the 1/2 together, plus a constant. Oh, oops. Rather, I mean bt cubed over 6. bt cubed, so 45t minus bt cubed over 6. And then, well, the initial position was 0. I'm saying that it started at position 0, and I'm trying to figure out how far it goes during this time. And I can plug in the fact that it stops after 6 seconds into this function for the position to figure out how far it gets during that time. So because the initial position is 0, that makes the c 0. I plug in 0 here, plug in 0 there, 0 there, I get the c equals 0. So the c equals 0, and then the position at time 6 equals 45 times 6 minus 2.5 times 6 cubed over 6. 45 times 6 is 240 plus 30, which is 270. And 6 cubed divided by 6 is 6 squared. That's 36. So I have 2.5 times 36. 36 times 2 is 72, plus 18 is 90, minus 90, and I get 180. So 180 meters is how far it travels. Delta x vector I hat, that's my result. Box that in and put that in mastering. So keys here, I've got an acceleration function that's not constant, it depends on the time. I've got an initial velocity, 45. I've got final velocity is 0 because I know it's stopping. I don't know the amount of time it takes. I don't know how far it goes. The acceleration vector is actually negative because the initial velocity was positive and it's slowing down. That's how I got the graph of the acceleration increasing in magnitude but pointing more and more negative. I've got the velocity decreasing like this, where it changes slowly at first and then gets more and more steep as time goes on. And then the position function is a cubic, where it's steep at first because you're going fast at first, and then you're slowing down, and you're slowing down more and more and more. So this should be more clearly a cubic. And then I did the integral of the acceleration to find out how much the velocity changed, used the constant to show where it started from, and got the full velocity function. Then I solved for the time that it took for the velocity to get to 0. It was 6 seconds. And then I later used that 6 seconds in here in the position function to figure out how far it got during that time. So even though this is slightly more complex because the acceleration isn't changing, there's still, in essence, the same basic pattern. I've got some information about the motion. I'm using that to set up the integrals or the kinematic equations to figure out the velocity change, and then the amount of time, and then how the position changes. And really the only thing that's different about this problem compared to others we did in this past week is that the acceleration isn't constant. So you really literally have to do the integrals instead of using the kinematic equations as they're written down in formula sheets. Let me know if you have any questions. Thanks.